Hey Calc students, time for another free response question from an old AP exam. Today we are looking at the style that is called table of values, and this one's actually a table of values with a little bit of PVA and maybe even two rates, kind of. But this is from the year 2014, and this is question number 4. So a pure non-calculator. And we'll read the question, get a feel for it, and then we'll attack. So here's what it says. It says a train A runs back and forth on an east-west section of railroad track. Train A's velocity, measured in meters per minute, is given by a differentiable function v sub a of t, where t is measured in minutes. Selected values for v sub a are given in the table. So I have the table right here, which I'm actually going to move around as we need space. So, for right now, it says train A, so you could presume there's going to be a train B. So let's just write a couple things down here just to remind ourselves. A couple notes here off to the side. They're giving us the velocity, so we are going to have a little bit of PVA concepts going on here. If they give us velocity, there's a good chance they're going to ask about acceleration or position. And we know that we derive to move to the right, and we integrate to go left. And then the problem also says this train is just, it looks like there's an east-west little loop it does. And so the train, it maybe doesn't, it actually just goes in reverse, but it's almost like a particle question. But it just goes to east and west and back and forth. And that's all it does. So that's train A. Now, since this isn't a particle, so you might be anticipating, you might be thinking, oh, is this sideways motion? Should I be anticipating that I'm going to use for position, my position function? So will position of t be written as x of t? That would be okay to do. It's not necessary. We typically reserve this for particle motion problems, x, but we can use s for this one. But so we're going back and forth. We don't have the velocity, but we have some values, and so you can anticipate whenever you see this table of values, we're probably going to be approximating the position by area under a curve, and we'll use one of the methods, either Riemann sums left and right or trapezoidal method. And maybe we'll see with the acceleration, since we don't have the function, we'll probably have to approximate with a secant line. You can start predicting what's going to happen. But it looks like we have a train going back and forth. We have some values of the velocity. So before we even look at the rest of the questions, you always just want to graph it to get a feel for it. Now before we graph it, you do want to notice, looks like we're going from 0 to 12, and this is in minutes. So our x-axis just needs 12 units, but the y values are quite extreme. We go to a high of 100 and a low of negative 150. So if you haven't picked this up yet, the fact that our velocity is negative, all that means is the position has changed direction, which really makes sense with this problem because it says it goes east and it goes west. So heading west would be left. There's going to be your negative 150, and the positives are when it's moving east. So this isn't surprising, but when you're graphing, you're going to have to account for it. So let's go up here and try to make a fairly decent graph, and we're going to have to make sure we have enough distance on our y-axis to graph appropriately. So I'm going to tuck this away up here, and so I'm going to make my y-axis about there and give our x-axis plenty of room here. And it's actually time, and we need 12, so let's see if we can put all 12 on here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So that worked out. And let's see if we can, we'll highlight the values they give us here. So we have a value at 2, that's important. And then we have another one at 5, so 3, 4, 5. And then we have one at 8, so 6, 7, 8. And then we have the one at 12 right there. Okay, then the y-axis scale's not super important here. The highest value we have looks like we go up to 100. We have another value at 40. Then on the y-axis here, we go down to negative 120. And we go a little bit farther to negative 150. Okay, so I'm going to put some points here. So at 0, 0, nothing, no crazy initial position. At 2 is when we go up to 100. 5 is when we drop to 40. 8, we go to negative 120. And 12, we are at negative 150. Okay, and again, that is our velocity function. And since the velocity changes sign here, we know that it's changing direction. Okay, so it's something kind of like that. It's it could have had some other changes of direction in there, but if they did, they probably would have mentioned it. But this is basically what we have, something kind of like that. All right, so now let's go ahead and see what they're asking for. So let's go to Part A. Now, since I have this kind of floating here, I think we're going to maybe we can we'll just move this around wherever we need to. All right, so here's Part A. Part A says find the average acceleration of train A over the interval from 2 to 8. It's average acceleration. Well, this is an easy question on one hand, but it's actually easy to make a mistake. Whenever you hear average acceleration, when you hear the word average, you think Algebra 1. And you say, oh, well, if acceleration right here, the derivative of velocity is acceleration, the derivative would be the slope of the tangent. So just for instance, what if they would have said find the instantaneous rate of change, or find the instant acceleration at t equals 2, you would have said, oh, I'm going to find the derivative. But since they're saying average, I need an interval. But you need an interval on acceleration to get the slope of the secant. So I think just so this isn't misleading here, I'm gonna make this a little bit more of a let's make this a little bit more of a peak like that. Okay, and so what we're gonna do is over the interval from 2 to 8, we're just gonna use this point right here, and we're gonna use the point that was at 8, and we're gonna find the slope of the secant that's going through here. Okay, so remember when it says average, it means we're gonna find the slope of a secant, which means we need an interval. So for the average acceleration, the average rate of change of velocity, we're going to, over this interval, we're going to have v of 8 minus v of 2 all over 8 minus 2. Okay? So you want to make sure that you understand the fact that they say average acceleration. You want to make a note that average acceleration still uses the velocity function. If you want to know the average rate of change of something, you use the function that you need to find the average rate of change. A very easy mistake would be thinking that these should have been acceleration, but they're not. This difference is giving you the average acceleration, but I'm using velocity. So now I just go to my table, and maybe we'll just move this up here for now. And let's see, v of 8 was negative 120, and minus v of 2 is equal to 100, and then our difference on the bottom here is 6. So it looks like we get negative 220 divided by 6. 2 goes into both of those, and we get negative 110 over 3. Now, this is not a particle question, so labels are important. And if you remember, since we're finding average acceleration, we're going to have to square our time units. And so this is in meters, so we can say meters per minute squared. Make sure you get that label right. Okay? So average acceleration still uses the velocity function. Make sure you catch that. Okay, Part B. Part B says, does the data in the table support the conclusion that the train's velocity at some time is negative 100 per minute? Sometime between 5 and 8. Give a reason for your answer. Let's go ahead and look at the graph. I'm going to take this secant off right here, just to keep the picture from getting too cluttered here. And so I'm going to show you these two values, and I'll show you what we're being asked to do. So at 5, I want you guys to look right here. At 5, this coordinate here is at 5 minutes, we have a velocity of 40. Okay? And at 8, the coordinate right here, at 8 minutes, we have a velocity of negative 120. Now, I want you to look at this. The velocity function is continuous and differentiable. Would it make sense that somewhere in this interval, from 5 to 8, somewhere in there, the velocity is negative 100? Well, if the function is continuous, then it definitely had to. In fact, it looks like negative 100. It occurred like maybe right there, sometime between 7 and 8 minutes. So if they're saying, does the data in the table support the fact that at some point we crossed negative 100? Now your answer to the question is going to be yes, but you have to justify your answer as to why. Now just a quick review on this one. Whenever you get this question, this is a pre-calc question. And I've done this several times. If you ever have a function, and I'll have a negative function like this, they like to do this where it's a and b. And if you remember, if this is f of a, and this down here would be f of b. They like to ask the question, does a 0 exist in the interval from a to b? Well, the answer is yes. And the reason it does is it's by the intermediate value theorem. So there's two big theorems they like to refer to, the intermediate value theorem and the mean value theorem. So for this one, the intermediate value theorem says if the function, so I'll call this f, if f is continuous and differentiable, on a to b, a less than, I'll put x less than b. If f is continuous differentiable on a less than b, then there is a 0, or an x-intercept, or f of x is equal to 0. There is a 0 in the interval, or by intermediate value theorem, f is continuous differentiable. Then I have more to say here. Okay, and f of a is positive, and f of b is negative. That's the key right there. If we have one positive y value, one negative value, then there is a 0 in the interval. Now I'm being really quick right here just to review this concept that you want to say, oh, that's right, the intermediate value theorem, if I have a positive y value and a negative y value and the function's continuous, well then somewhere in that interval had to be the 0, and we would call it the c value. Okay, that is what they're wanting you to apply here. So this concept, you look over here and you say, well, yeah, if the one y value is at 40, the other one's at negative 120, negative 100's in the interval. So I just have to state that. So the way I want to say that here is, so if, I'm going to start with my if statement. So if v, and I'm going to use the subscript a because this is the train A, train B is coming up. So if v sub a is differentiable and continuous, and that is on our interval here is 5 to 8, 5 less than or equal to t less than or equal to 8. So if v sub a is differentiable and continuous, okay, if it is, and v, and I'm going to use v of 5, and v sub a is of 5, I changed my mind here. I like to use less than statements here. I'm going to use a v sub a of 8 is less than negative 100, which is less than v sub a of 5. Okay, so if v sub a is differentiable and continuous, check, and the velocity at 8 is less than negative 100, which it is, but the velocity of 5 is greater than negative 100, it is, then by the, and you can just say IVT, intermediate value theorem, but I'll say intermediate value theorem, there exists a time in the interval 5 less than t less than 8 such that v sub a of t is equal to negative 100. Okay? So it might seem just kind of intuitive as you look at it, but you struggle with how to articulate it, and that's not uncommon. So just be prepared if with the intermediate value theorem, they love throwing this at you, intermediate value theorem and mean value theorem. And it just, if you're like, gosh, I know that, of course it would have to, because it's got to cross that value, that's your trigger that you're like, oh wait, that's the intermediate value theorem. So just say, okay, here's my if. If I'm differentiable and continuous on the interval, got it. And if the y value is higher or greater than the y value they're looking for on one endpoint, and the other endpoint it's less than what they're looking for, if I can say the y value they're wanting is in between the ones I've got, I state that here, then by the intermediate value theorem, there will be a value in the interval such that the velocity at a certain time will equal that y value. So we're just trying to state that it exists. Okay? So there it is, the intermediate value theorem. And that's 2 points. Okay, let's move on to C. All right, so C says, now we're getting to the more guts of the question. It says, at time t equals 2, the train's position is 300 meters east of origin station. Okay, well, I'm just going to write that little piece of data. I'm going to jot that down over here. And I like to do, I'm just going to put position. I'm going to say the position, they're telling us, at 2 is equal to 300 miles. Or is it meters? At train t equals 2, the position is 300 miles east. So it's going this way, okay, east of the station. So if we said like the station was right here, 300 miles east, so it's a positive 300. Now, it's interesting that they say that because we don't have, or we have the information about the velocity at this spot was 100, but the position is 300, okay? The train is moving to the east. Write an expression involving an integral that gives the position of train A in meters from origin station. So let's just do that part of the question. There's more. So this is the fundamental theorem part of the question. So we have to set up something we know. So they just gave us position 2. That's a huge, huge hint. We're going to need that. And what they want to know is where's the train at the 12th minute. So what we're going to do is we're going to set up an integral. And we're going to say, well, if we integrated from 2 to 12, the velocity, let's see what we would get. So this is a common concept right here with PVA. We're integrating the velocity, and what that's going to give us is the position. The position at 12 minus the position at 2. Now I'm just using this is my own little notation here, position, but what you'll want to do is say, well, I'm just going to use S. That's the variable they like to use. So the position of train A at 12 minus the position of train A at 2. Okay, so I'm just showing you that means position. Now, in the question, they just told us right here the position of the train at 2 is 300. So we know that these are 300 here. So now that you see this, I'm actually just going to erase this for notation's sake. So just position. Position is S of A, so I'm going to jot that down over here, just notation-wise for me. So when I say the position of the train at T, that's equal to S of T. Okay? So I'm going to just simplify this a little bit and just rewrite this so we don't have too cluttered a picture here. So this is going to equal S, the position of the train at 12, minus the position of the train at 2. Okay, now this is what they want. They want the position of the train at 12. That's what we're solving for. So I'm going to take the initial position and add it over here. So what I get is the initial position of the train plus the integral from 2 to 12 of the velocity of the train. And that should give me the position of the train at the 12th minute. Now, the position of the train at 2 is 300, so I'm going to replace it with that. So here would be my final step for this one. I would say 300 plus the integral from 2 to 12 of v sub a of t dt is equal to s sub a of 12. That is my integral expression to explain where is the train at the 12th minute. Okay? Now, you may skip a step here or there, but I just wanted to, I don't want to lose anybody in the process. So this is the expression they're looking for. Okay? 300 plus integral 2 to 12 v sub a of t dt. There it is. Now, the rest of the question says, well, after we do that, it says, use the trapezoidal sum with 3 subintervals indicated to approximate the position of the train. Now, if we had this, if we had the velocity function, we could just integrate it, but we don't. So now they want us to approximate. So that's a little tricky on this one because we have a positive and a negative part, and we only need to do it from 2 to 12. So this picture is going to look a little bit weird when I do this. So I'm actually going to switch here to, I think we'll do orange here. And so I want you to see the trapezoids that we're going to make here. So I'm going to go to 2, and I'm going to draw a straight line down here, okay? and I'm going to go to 5, which was already sitting here from before, from that other part of the question. Okay. And we're going to go to 8, and we're going to make this one down. And then we're going to 12. Okay. Now this one throws students sometimes, and the reason it does is because we have this positive and we have this negative portion here. So 2 of the trapezoids are fine, but the third one is kind of weird. So with the trapezoidal method, I'm just gonna approximate this. I'm topping this trapezoid, so we're gonna find the area of that one. And people are okay with that one. They say, okay, and I've got this trapezoid down here, and that's going to be negative because we're below the x-axis. But it's this weird one right here. You're like, how in the world? How do we do this? Well, geometrically, I would be connecting this point to this point. I don't even make a trapezoid. So this is kind of weird. If I connect those 2 things right there, and then I connect these right here, I have this, I have part above and part below. Now, what you don't want to do is you don't want to divide this up and make it 2 triangles. Don't do that. So just want to remind yourself, treat as a trapezoid, and I'll show you when we do the work over here, okay? So I know this looks weird, but trust me, it'll all work out area-wise. This one will be fine, this one will be positive, this one will be negative, and it depends which one's more positive or negative, what happens here. So we're going to do that area, and we're going to fit that in right here, and let's see what we get. So the area of a trapezoid, if you recall, is 1/2 base times height. So I think I'm going to start this and fill this in here. So the area of the trapezoid, so by the trapezoidal approximation, so I'm just going to say my trapezoidal sum. So my trapezoidal sum is approximately, let's just look at the first one. So it's the average of the bases, and the bases are vertical for this. So it's the average of those 2 things times the height, but the height is the width because the trapezoid is sideways. So just to remind you from geometry, normally in geometry we do this, and we say this is B1, this is B2, or vice versa, and the height we would be calculating. Okay, but for ours is sideways here, so we have this kind of trapezoid. So this actually is the height, and our bases are the y values there. So we're going to average those times the width, but it's the height for the formula. So let's look at the first one. So let's do the average of the heights here. So it's going to be the y value at 2 and the y value at 5, and then we just go to the table here. And so we have 100 plus 40 divided by 2. There's the average of the bases, which are actually heights, times the width of this thing, and 2 to 5 is 3. There is trapezoid number 1. Okay? Plus trapezoid number 2, just follow the rule. Now, even though one's positive, one's negative, I promise it'll work. So what's the height at 5? That was 40. What is the height at 8? That's negative 120. And what's the width of the interval from 5 to 8 is, we're going to need the average of that. Okay, and now times the width of that interval, 5 to 8 is 3. Okay, the third one, now we're to here, at 8, again, we're negative 120. And at 12, we are negative 150. The average of those 2 times the width of that, 8 to 12 is 4. Okay, so you want to make sure you understand how each one of these trapezoids was taken. And now it's just a matter of simplifying. So I'm just going to keep going across the bottom. So the first one here, we get 170 divided by 2 is, 140 divided by 2 is 70. So we get 70 times 3 for our first one. So 70 times 3, that'll be 210. We'll do that in a second. This one, we get negative 80 divided by 2 is negative 40. And so the second one is negative 40, and that one's times 3. And the last one here, looks like we get negative 470. So that's looking like. Divided by 2, or sorry, negative 270. Negative 270 divided by 2. So I believe on this one we're going to have 135 times 2. But we have this, these are even on this one, so let's go ahead and cross cancel. So this 2 will cancel with that 4 and make this a 2. So that's going to reduce to a 2. So we have 2 times 270. So I'm going to put 270 times 2. Okay? And then I'm going to put their work above. So this winds up equaling 210. Plus this winds up equaling negative 120. And then plus this winds up equaling, oh, this was a negative 272, by the way. So this winds up becoming a negative 540. Okay, so positive 210 minus 240. So if we just combine the negatives here, looks like we get 210 minus this becomes 660, I believe. Right? So 660 minus 10 is 650, so we get negative 450. Okay? So the trapezoidal sum for all of this part was negative 450. Now, you got to be careful because negative 450 is the most common wrong answer. Because negative 450 was, and this is where you get burned, it's just kind of an annoying deal. Negative 450 was just this part of the integral. But you have to remember there was this initial condition, or initial position, or it was at 2 actually, it was 300. So negative 450 is the value of the integral, but don't forget the 300. So my final answer right here, so my approximation for 12, okay, the approximation of the position at 12 is equal to 300 minus 450, which is equal to negative 150. Okay, and that is meters. Now, if you want to be really picky, since it's negative, you must have been going west. Okay? So, once again, from the top, we had to approximate position 12. We had to manipulate this with the fundamental theorem. Make sure you put the position at 2 on the other side. That was 300. Estimate using your trapezoidal sum. Reviewing that process right here. Simplifying it, and don't forget to add it to 300 when you're all done with that, and your final answer, negative 150. Okay? So there we go. So the last part we have is part D. So for part D, to give me some space here, I'm going to erase what we have here, and we will polish this one off. So the table of values tend to be a little time consuming, especially as I'm explaining them. They take a little bit longer to get through. But hopefully that's making sense to you. All right, so I'm going to just block this off so we don't have any confusion here. All right, and this, block that off too. So here's my last part for D. All right, let's see what D says. D says, a second train, train B, travels north from origin station at time t. The velocity of train B is given by v of b is equal to, so we actually get a velocity function. So train B has its own function, but we get it this time. And it's a relatively simple one. It's a quadratic, because this is a no calculator question. So we're probably going to have to manipulate this. So negative 5t squared plus 60t plus 25. Okay? And at time t equals 2, the train is 400 meters. So what I'm going to write here is S sub B, because it's the second train. The position of the second train at 2 seconds is, or 2 minutes, is equal to 400. Okay, versus up here, the position here of train A. In fact, I'm going to write that here. Remember, the position of train A at 2 was equal to 300. Okay, so that was from earlier. But for train B, it's at 400. And it says, find the rate in meters per minute at which the distance between A and B is changing at t equals 2. Okay, now if you haven't done one of these for a while, it can seem very difficult, but really these were done way back in the end of chapter 2. This is a related rates question. So I'm going to draw the picture, and you're going to see they give you so much information, it's actually pretty friendly. So here's what they're saying. Here's origin station. So creative, aren't they? Origin station, we have train A is going this way for 2 minutes. Well, you guys, all of these values were really handy. And train B is going north, it says. So this is train A, okay, and this is train B going north. And what they want to know is how far apart are the trains getting. Okay, so I'm going to call that, I'll go ahead and call that C. Or change my mind, I'm going to call that D. What is the distance the two trains are apart? Okay, so this one after 2 minutes, this one's heading east, train A. Train B is heading north. Okay, so if you remember related rates, we have to come up with an equation, and then we have to take ddt of it and all that stuff. So this is just a Pythagorean theorem question, and this is just refreshing your memory, refreshing your memory of this approach and these kinds. It'll come back to you. It's not quite the latter question because d is changing. And so if you looked at this, you would say, oh, well, I think it's just the Pythagorean theorem. So I have a squared plus b squared is equal to c squared. That's true. Now what I'm going to do to that equation is I'm going to take d dt of it, because it's a related rates. So this is going to become 2a, variables don't match, I have dA dt, plus 2b, variables don't match, dB dt, equals, sorry, I called this a d, didn't I? Equals 2d dd dt. So all I did was took the derivative of those with respect to t, so I implicitly derived those. Okay? Now the first thing I'm going to do, just to make these easy, I'm just going to go in here and knock off the 2's. Just divide everything by 2. I don't need those there. It just makes the problem more complicated. Don't need them. So those are gone. Okay? And so here is my equation. Okay, well, what's important here to know is that this question is all done at 2 seconds. Non-calculator question, they have to give you friendly things. Well, look at how nice this works out. Train A, going this way here. Okay, this is train A. I'm going to tweak this a little bit. This is train B. Well, train A at 2 minutes. Train A at 2 minutes, it says that its position, we already know this, the train is 300 meters from origin station. And if you read closely here, it says at time equals 2, train B is 400 meters north. They gave us all we needed to know. So that's 300, that's 400. Hopefully you remember this from geometry, if this is a 3, 4, 5 right triangle. So really, A was equal to 300, B was equal to 400, and D was equal to 500. And then dA dt is the rate that it's changing. Well, at 2 seconds, we can go to the table. And so on this one, the rate the train is moving after 2 minutes, dA dt from the table is 100. Okay? After 2 seconds, we're going to figure out what dB dt is. At 2 seconds, we're going to have to actually figure it out up there. And the question is, what is the rate that the trains are moving apart from each other? That's the question. So what I'm going to do over here, I'm going to figure out what is the velocity of train B at 2 seconds. So it's -5 times 4, because it's 2 squared, plus 2 times 160 is 120, plus 25. So it looks like we get -20 plus 145. So it looks like it is 125. So the velocity of train B at 2 minutes is 125. So I'm going to put that up here. Okay, let's start this from the top here. All right, so here's the situation. At time equals 2, train A is heading east, train B is heading north, and they want to know how fast are the trains going apart from each other. So I have a right triangle, so my equation is the Pythagorean theorem, right triangle, a squared plus b squared equals d squared for the hypotenuse. I take d dt of it, so I get 2a dA dt plus 2b dB dt plus 2d dt. I just knocked out the 2's. And so now A is the distance, B is the distance, D is the distance. I have all of those. I was given those, or I guess I was given A, and B, I had to solve for D. I have the rate both trains are going. I had to solve for this velocity, but this is actually what I'm solving for. So I'm going to now put in the 5 things I have and solve for the one thing I don't. So A was equal to 300 times the rate it was changing, which was 100. Its velocity is 100 from the table. Plus train B was 400 meters north times the rate it was changing. We calculated that to be 125. And the distance is 500, but what we're solving for is what is dd dt. That's actually what we're going to solve for. Okay, so 300 times 100, we're going to have a 3 with 4 zeros here. So we have 30,000. And then plus 4 times 125. I believe on this one, what are we going to have? 50,000? Is that right? Right, so 4 times 125 is 500, and then plus 2 zeros, so we're there good, 50,000. And this is equal to, again, 500 dt. All right, so what do we wind up with? 80,000 is equal to 500 dt. Divide both sides by 500. So let's see, 80,000 divided by 500. So we'll cancel our zeros there, and then it's 5 into 800. So I'll do that. I'll do 800 over 5. And if you divide that in there, I believe you're going to get 160. Okay, and then we just have to make sure we get our label right. So the distance, or the rate the distance between the two trains is moving at t equals 2 is equal to, they are separating at 160 meters per minute. Okay, and there that is. So you could see this is pretty full problem here. I've been working on this for a while here. First one, it wasn't just a straightforward table of values. It had a table of values mixed in with a little related rates question here. So this one was a pretty beefy question with a lot of skills. So again, from the top, approximating acceleration, knowing it's the slope of the secant. The second one, intermediate value theorem. Third one, probably the more straightforward of them, fundamental theorem, area under the curve, but it was approximating with the trapezoidal rule. And then D was actually its own little related rate question. Could almost have stood alone. So pretty long question, a lot going on there, and that is 2014 question number 4. So thanks for watching. We will see you next time.